Você, quando você começar a gravar, bom, eu devo falar aqui uma frase aqui. Essa apresentação está sendo gravada. Esta apresentação está sendo gravada e será disponibilizada publicamente. Por favor, mantenha os vídeos e os áudios desligados. Caso desejem se identificar, vocês automaticamente concordam com a divulgação pública da manifestação. So, good afternoon, everybody. Today, it's a pleasure to have here Professor Jeffrey Ping Liu from University of Texas at Arlington, USA. Professor Liu received the PhD degree in physics at the University of Amsterdam. He is a distinguished university professor at the University of Texas, Arlington, USA. For the past 4 decades, he has worked in research and development of permanent magnets and related magnetic materials in China, Europe, and US. His recent research has been focused on hard magnetic nanoparticles, thin films, and bulk nanocomposites, as reported in his more than 320 peer-reviewed journal papers. He has supervised more than 50 graduate students and postdoctoral researchers. He is an elected fellow of the American Physical Society and the IEEE. He received the Outstanding Achievement Award at the 25th International Workshop on Hard Earth and Future Permanent Magnets and their application in 2018. Today, Professor Liu is here as a distinguished lecturer from IEEE. So this program from IEEE nominates almost four distinguished lecturers that give almost between 20 or 40 lectures around the globe. And the objectives of this distinguished lecture program is mainly to celebrate the achievements in magnetics and honor the finest researchers and communications in the field, to provide outstretch to the wide community and promote the transnational aims of the Magnetic Society, to support chapter activities by providing high-profile speakers for local meetings, to inspire and excite especially young researchers, enter in a career in magnetics, and to advertise and promote the IEEE Magnetic Society as the society of choice for magnetics professionals. So, it's a pleasure again to receive here Professor Liu. Thank you very much for your talk today.
Thank you. Can you hear me? Yeah. Thank you, Leb, for your very kind introduction. First, I apologize I cannot speak in Portuguese. This is also my first time to visit this country. Everything has been so great. Michelle from Rio, to Campinas. I hope the pronunciation is correct. When I came to the very nice campus, I found this is very, very special gate. So this is a gate very significant. So people in this campus, like you guys, really good luck. I appreciate what you have done, and it's very beautiful campus. Having me today, so thank you very much. I also thank the IEEE Magnetic Society, as mentioned just now. I'm lucky and invited to give these distinguished lectures in this year. This has been like something come back because in the pandemic time for more than 3 years, we had this lecture systems, but we could not talk face to face like we do today. So I also very appreciate Japanese society. I will also explain a little bit about this logo. Okay, this is looks like a spoon for soup. I know the food in this country is just wonderful. I will explain. Then the title, I assume most of you in this room very familiar. Okay, if not, I'll just explain a little bit. Magnetic hardening. The hardness in magnetism is not mechanical hardness. Okay, but I will explain what means that magnetic hardness. Low-dimensional is a description of the size. Okay, I will also explain a little more. Ferromagnets, when we talk about something magnetic or non-magnetic, we have to be careful. Okay, if we say something is magnetic, something is not magnetic, that's wrong. Actually, everything is magnetic because everything is diamagnetic, right? If you have taken that solid state physics. However, in most cases, we only talk about the ferromagnetic. Why? Because diamagnetic or paramagnetic, that's very, very weak. Okay, so we usually do not consider them as a real magnetic. Only ferromagnetic. What do you mean by ferromagnetic is all the magnetic movement are aligned to one direction. So the strong magnetic movement or strong magnetization. Okay, that's the beginning. Now, let's explain this logo. So this is not a spoon, but it's a campus. Why I'm interested in the campus? Because this is the earliest permanent magnets. Okay. What is permanent magnets? If you have a piece of ferromagnet, magnetize it, then if the magnetization can be kept forever, we talk about forever, but nothing is really forever, but if you can keep your magnetic moment for a year, for example, then we call this as a permanent magnet. If you magnetize it, but after you remove the magnetic field, then the magnetization immediately disappears. We call that a soft magnet. Okay. So that's the difference. So the earliest permanent magnet is the campus used in Asia and China 2,000 years ago, something. Okay. Campus means the device that directs the direction. Okay, indicates direction for aviation, for example. When earlier European people immigrate to these continents, they must use something to find the direction. This is the version 2.0, I think. This is not as old as 1,000 years, probably 100 years. What they use in China is not only for point directions, but also calculate some astronomy details. Of course, I don't have time to go all the details. Be honest, some of the words I cannot read all of them, but I can read most of them. If you are interested, you can Google, you can check. Okay. Campus has been important, and permanent magnets is also very important. So let's start with the more scaled introduction, and then talk about some fundamental ferromagnetism, because here, in this room, most of you are interested in magnetism, condensed matter physics, right? if you have noticed that ferromagnetism has been strongly size dependent. Okay, and then I will introduce our work on experiments, the nanoscale or low-dimensional hard magnet materials. Then I talk about something quite general, outstanding issue about hard magnetic materials research, which is related to coercivity. I will explain more. Okay, I hope I can finish it certainly before midnight. if you are patient. Okay, this is the applications of ferromagnets. Okay, I think nobody in this room, in this campus, probably also in this country or in this world, who can say, okay, I know nothing about ferromagnets. I don't care because I do not use it. But now I think everybody uses it. If you do not use motors, you use cell phone, you drive a car, and you use computer, hard drives, or you use electricity generated from windmills, or you take some city transportation, or if you do not do all of this, you probably will go to hospital eventually. Then use of the devices, okay? And the figure of merit of ferromagnets called energy products, which is calculated according to the square area in the second quantum of the, we call it magnetic hysteresis loops. I just visited your very well equipped laboratory. I've seen how many magnetometers you have, at least 6 of them, right? Yeah. And you guys are so rich, you speak the hell, which surprised me. I visited many labs in the world. Most of the labs give up the little helium magnetometers because the helium is so expensive. So I'm happy you are still running the little helium, but maybe in the future I send some samples for you guys to measure for free. Okay, for permanent magnets, you can see in order to make this square larger, you have to have both large permanent magnetization, called PR, and coercivity, HC. The coercivity is nothing but the ability to resist demagnetizing. Okay, so the earliest permanent I mentioned, the campus. Okay, if the campus is not hard enough to resist the demagnetizing from the Earth's magnetic field, you know, we are living in magnetic field, Earth's magnetic field, then they cannot keep the magnetization all the time. Okay, then you cannot use it. Okay, so how strong is the Earth's magnetic field? Student here is weak, about 2 to 3 oscillators. Okay, so then for the campus, they have to have a coercivity larger than 3 oscillators for sure. The best is if the larger, the better. Okay, the larger of the HC, the larger of this square. So the larger the better, right? All the stories from here. Okay, for this talk. So the figure of merit of ferromagnets has been increased very impressively in the past 100 years, starting 1910. I hope you can read this. Starting from the carbon steel, which is based on iron. We consider iron as a soft magnet. Okay, however, you can do something to make it hard. That's the magic here. Okay. That's the magic here. Okay. I mentioned that campus, the earliest magnet ferromagnets, but the campus is here. Okay, the coercivity is very low. What we can see today for ferromagnets is only after the Industrial Revolution started in Europe. After that, we start to produce in the industrial scale mass production of ferromagnets. Okay, that history started from here. And the history of my research in its hard magnet materials started from here. When the neodymium iron boron magnets was just invented in the earlier 1980s. So you guys know how old I am. I'm older than you, huh? Okay, so here is about now 30 years again now. Okay, so from this chart you can see that the development of ferromagnets is really based on two things. One, number one, you have to find the different new materials in order to make the performance higher and higher. Number two, you have to improve the existing materials step by step. Okay? I think for most materials, we did it a similar way, right? And I want to show that this chart has been quite popular. I think many of you have seen this many times. But this was not so common to see. Actually, I asked my postdoc recently collect many data, also from the historical literature. Then we found, okay, the time scale is about the same as possible. Okay, then we found the history of ferromagnet development is really the history of the enhancement of coercivity. Okay. What is interesting is you can find many different ferromagnetic materials. You can pick out the mine. I know there's many mines in Brazil. You have a huge deposit of rares, is that right? You're the number 2 rares deposit in the world. China is number 1, Brazil is number 2. However, any lateral materials have no coercivity. You have to do many things to develop a coercivity to make magnetic, to produce magnetic hardness, to make it magnetic hardening. Yeah, that's the story. So earlier magnets always shaped like the horseshoe. Why? Because in that shape you can have the south pole protect the north pole. So they want to be easily demagnetized. Now you see less and less magnets this shape. Why? Because we have the new magnets hard enough, okay, with coercivity high enough. So there's no worry that they will get demagnetized, okay? So it can be any shape. The simple shape is just a cylinder, right? For example. However, if your coercivity, if your energy product is not high enough, you have to make the cylinder really large to have enough energy. That's 200 years ago. We have the ferrite based. Then in 1950s, Phillips research discovered the hard magnetic ferrite. That's not the earliest, but that's the early industrial scale permanent magnets. Then in the 1980s, as mentioned, when I started to do something, like the young people in this room, the rares, this is neodymium iron boron permanent magnets. Okay, so how strong is the neodymium unborn ferromagnets. Here I show that this is a figure from the National Geography. Okay. This is a magnet. It can easily handle 1 kilogram of a ferromagnet. Okay, 1 kilogram. So you know how, you know what means the hardness, what means the energy density, why they make a difference. Okay. Not everybody is clear about this story. Okay, what I mentioned. Okay, and even in National Science Foundation in the US, I saw a book that's 50 years ago. This is energy-related materials. The whole list did not include magnets. The list. That's obviously wrong because we use half of our energy for energy conversion. What do you mean energy conversion? Motors. Okay. We change we convert electric energy to mechanical energy. That's what we do, motor. Then generators is in orbit in many cases. Okay. Like a lot of hydropower plants in this country, right? We use the mechanical energy, we convert the mechanical energy into electricity. Okay. If we have the good magnetic materials in those devices, we can make it smaller, lighter, and stronger, okay, at the same time. So, of course, there's energy with the materials. Now more and more people realize this and accept our, our education, okay? We organized this review paper. In 10 years, it has been cited almost 3,000 times. That's my young time. I told you guys when I started my research on magnets. I did my PhD in Holland. 3 days ago, I talked to this one of the colleagues in the Center for Physics. He showed me my PhD thesis because his wife was also studying in University of Amsterdam at that time. My friend, my thesis, I sent a copy to her, and he took this to my lecture, which is a big surprise for me. So what I did in my PhD research is we measured so many various transition metal compounds. I don't know how many of you are doing PhD now. You really have to know that the PhD study is very hard. It's very hard. And you have patient enough. Here I just list one table in my thesis. In that lab, we measured altogether 40,000 of the compounds. I measured more than 2,000 of the compounds, right? Because we want to scan all those compounds in order to find new material that is even better than iodine and boron. However, in 30 years, we still have not found another one. I'm getting retirement. We have to do something different. Okay? So the search is still going on. People are like what I did, okay? To scan all the materials. And now we are using the machine learning, AI, to make the search even fast. Not to all this measurement, okay? To see if the computer can find it faster than the human, okay? So that's one approach. Another approach is we call the metamaterials. We don't have to find the new phases or new compounds. Just to use the existing hard phase and soft phase, mix them together. That can give you higher energy products. the physics is simple. You have the hard phase, soft phase, mix them together, you get this hysteresis loop, okay, which I showed you. This is second quantity, right? And with a large area, okay. However, the physics is simple, but materials processing is not simple. I think many of you in this room agree with me, because experiment processing can go very wide. So you have to do a lot of dirty work. Okay? If you just mix them in a random way, the exchange coupling won't take place. What you obtain is the blue loop. See, it's a big kink. I don't know how many of you, when you measure your loops, you get these kinks. Very common, actually. Okay. In this case, the mixture of hard phase, soft phase is a superposition of the two loops. Okay. Mathematical superposition. There's no exchange coupling. So in this case, you won't have any enhanced energy product. You either get energy product of this or this. Okay. So that's not what we want to do. Okay. In order to make the exchange coupling take place, you have to reduce the soft phase dimension to twice the domain wall thickness. That's in 1930s, early 1990s, calculated by 3 groups of theoretical calculations. Okay. So this is the important step. Why? We are forced to go to the bottom. What is the bottom? Bottom is the nanoscale. Okay. When I start my magnet research in the neodymium and polymers, the grain size was 30 microns. That's the lowest grain size we could reach. 30 microns. 30,000 nanometers. Okay, you see the orders difference. Okay, now you need nanometers, because the domain wall thickness is a few nanometers. Okay, that's the physics. That's the physics. Okay. Now let's do a little bit more about this physics. This is Professor Feynman, the Nobel Prize winner, if you know this name. Okay. He was the first guy who draw people's attention about nanotechnology. He said there's a lot to play at the bottom. Okay. He was first mentioned that, okay, let's imagine you put an encyclopedia to adjust the coil. Okay, what's that coil? At that time, that's 50 years ago. Okay, at that time, people had never imagined that's possible. But it is possible now, right? It is more than possible now. We put many things in a small USB, right? And so that shows at the bottom. What's the bottom? Is the low-dimensional materials. Okay, good example is carbon. Okay, we call this variance of the zero dimension material. Why? Because in all the directions it's very, very small. So it's no dimension, we call it 0 dimension. Nanotubes, in one direction is very long, so we put 1 dimension. Or 2 dimensional, this in 2 directions very large. Okay, layers. Or 3 dimension, which we already know, graphite for a long time. So in this 3 low dimension carbon substances, they already 2 Nobel Prize. Okay. Actually, this can happen with any materials, right? Any substances, any compounds. Just we have not had time or money to do that research. Okay. For example, for gold, okay, if you have a big piece of gold at home, okay, then you can test if you keep reducing the size to nanometers, the property will change. For example, the metal point will go down this way. That means you can easily melt all your gold at home. Okay, it's not need high temperature. And this is physics. Okay, for ferromagnetism, this is very true. Why? Because many of the physical interactions strongly size dependent. For example, the electronic exchange interactions in angstrom scale and RKKY, if you're familiar, around nanometer. Then domain wall thickness, I mentioned already, right? From a few nanometers, okay, to 100 nanometers, depending on the materials. Okay. Then we have the particle size, domain size, and particle size. Domain size. Okay. They came in different size, no matter you like it or not. So that's the nature, that's the physics. Okay. Because of this ferromagnetism dependence on size, then we will find the properties of ferromagnetic materials strongly depend on size. One example is the theoretical paper by Dr. Byton in 1970, 72, 73, I don't read it. Maybe the young people can read it. He developed a mode called finite size effect, which is quite famous. He predicted that, okay, by calculation, say, Curie temperature of ferromagnet will change with size in this way, which is a little bit complicated. In 20 years, after 20 years, the first experimental proof of this was done in thin films, okay? We changed the thickness of these thin films. They did match Curie temperature change this way. Okay, this is a good experimental proof. However, thin film is a 2D material. Then how about the 0T material? Is that also follow that finite size effect? Okay. But we already know for quite a while when we dealt with micro-sized particles, we know when we make the ferromagnetic materials smaller, back to 10 years ago, or 30 years ago, when I was young, we could reach micro size, but not nano size. Okay? We already realized that the coercivity, which is the main topic of this talk, okay, can change with particle size. Okay, first, if you keep reducing the size, first it goes up and then goes down, reach the peak when the particle size is called single domain size. What do you mean by single domain size? Each particle has only one magnetic domain. Okay, so that has been already known. And later on, when we are able to make the particle size smaller, we found to some extent the ferromagnetism, or we call it hysteresis of the material, disappeared. It became like a paramagnetic material. What does it mean? Paramagnetic means you don't have any coercivity. Okay? Maybe for soft magnetic material research, they are happy. However, the paramagnetic material is not what we want for many cases, for applications. We still need ferromagnetism because the moment is high. Right? So, in this case, we try to understand what happens at this point, especially in case of a magnetic reporting, if you know that. we want the coating density higher and higher. That means you have to reduce the bit size smaller and smaller. Okay? But then you meet the superparamagnetic barrier. Okay? You hit it stop. Okay? So in order to do this, we have to have a good understanding why superparamagnetism takes place, which is actually simple. Okay? The formula is if we have anisotropy constant of the material times the volume, okay, large to the Boltzmann constant times temperature. Okay? Because the thermal fluctuation increases with temperature. Right? Just like the waves on the ocean. Okay? If your boat is too small, someday it will turn over and sink. Okay? But if you have a big ship, then it's no problem, it's safe. However, we want to have our boat as small as possible, but still stable. Okay, that's the game we want to play. Okay, that's a challenge we have to meet. That's why we are here, right? So, to understand this, all the details, we collect those typical ferromagnetic materials, okay, from relatively soft to the hardest. You know the hardest ferromagnetic material is samarium cobalt. Samariums are rivers, okay. The blue ones are the superparamagnetic size, and the red ones are the single domain size, okay. This size is calculated by the spherical shape. However, another big issue came. Okay. However, we found at the bottom the shape plays huge role. Okay. It's also difficult to control the shape at the bottom. Right? It's so small, we cannot see it. We have to use a microscope, like you guys are doing in the facility center. Right? For example, if you have your shape change from spherical to a nanorods, we call it rods, like this. This diameter can be much, much smaller than this diameter for superparamagnetic transition. Okay? Is that important? Yeah, it's very important to know that. Okay? Now come to the experiment class. When I started the experiment effort for the magnetic nanoparticles, I read the review article by Professor O'Connor at the University of Oregon. He already passed away again. He was a very good magnetochemistry experimentalist. He summarized all the available magnetic nanoparticles, ferromagnetic nanoparticles, by the time of 2002. What you can see is most of those materials oxides, iron-based oxides. Why oxides? You know, oxides is part of ceramic material. Yeah? Ceramic materials can be stable, okay, easy to synthesize. However, as I listed in the chart, the hardest materials are not oxides. The hardest ones, rings containing materials. Okay. So we start with composition iron platinum. That is good hard magnetic materials. We start with particle size 2 nanometers, increase 1 nanometer by 1 nanometer. We could control the size with the accuracy of 1 nanometer. This is TM microscope. This is XRD. You can see the overall picture. So you see the particle size change. Right? And for iron platinum materials, which people are very interested in it. Why? Because This is the material we use to replace cobalt materials in our hard drive. You know, we still use a large amount of hard drives in our clouds. Okay? In several phones, in laptops, we use solid storage now. However, in large drives, data storage, we still have to use magnetic code media. Cobalt is not hard enough, as I already showed you. However, as synthesized iron platinum materials, the nice looking nanoparticles, okay, they are FCC structure, if you are familiar with that. It's disordered arrangement of all the atoms. Okay. In order to make it ferromagnetic, you have to do heat treatment to realize the phase transition from the disordered FCC to the ordered tetrahedral structure. However, you must agree that when you heat up a bunch of very fine particles, they will center together automatically. Okay. Then you mess up everything. Okay, because we need these monodisperse nanoparticles, but now you come any kind of sizes. Okay. In order to solve this problem, there are many approaches people have tried about 10 years ago, like surface treatment, doping, coating, all of those. Okay, what we did is very simple. We just mix those particles with salt powder, with salt powder, table salts, okay, sodium chloride. You can buy it from supermarket. Okay, then mix them together to do heat treatment, then drop them into water. Then the salt is gone, right? Salt is the best for salt in water solution. Then what you recover is the particles after heat treatment. They're still monodisperse. Okay, and in order to know if this already phase transition, you can do XRD, you can do magnetic measurement, of course. Then magnetic measurement show that these particles have very high coercivity, up to 3 Tesla. So I call this the smallest ferromagnet. No one can go even smaller. Why? Because then you will reach the superferromagnetic limit. Okay, and this treatment method can still keep the shape of the nanoparticles after the long heat treatment. It's the temperature of 700 C. Now, go back to the story about the finite size effect. Can we have these ferromagnetic nanoparticles with 0 dimension that can follow the finite size effect? The answer was not clear. We saw the direction with Curie temperature. However, it is not consistent with the experiment extrapolation to the Parker material. What happened is we found, okay, the chemical or degree also changes with size. I know you guys do magnetic nanoparticle research. When the size reduce, okay, the crystal structure will be affected. Okay, it happened here. So then you have to distinguish 2 interplay factors to separate them. What we did is we did separate them. Then, for the first time, we proved experimentally that the finite size effect doesn't exist in the 0 dimension nanoscale ferromagnetic materials. So that is good progress. Then we tested these very fine nanoparticles down to 2 nanometers. Then we proved that, okay, when your size is so small, the magnetic ordering, the chemical ordering never take place. So that's what at the beginning we expect that, okay, at the bottom there are many things new, many things we do not know. Now we know. Okay. With those good ferromagnet nanoparticles, then we can start another project. Okay. We wrote proposals, say, let's do the nanocomposite material, which I showed you very quickly. Right? Instead of using top-down approach, which by rapid quench, I think many of you are familiar. Then we can start to see if the bottom-up approach will work or not. Bottom-up approach means we start the building from the bottom. Okay. Here is the proof of concept. If we mix the hard phase particles with the soft phase particles, if the particle size difference is not that big, for example 4 nanometer, 4 nanometer, 4 nanometer, 8 nanometers, they will self-resemble them together. That means each hard phase contact with soft phase. Okay. Then you have very effective exchange coupling. If the particle size difference is too large, okay, you see the segregation, then you get the big peak. Okay, as I showed you at the very beginning. Please note that the segregation dimension is not very big. Here is 20 nanometers. The whole range is 100. I can go without this, but because I'm a professor, I'm a teacher, I often talk very loudly. Huh? It's okay, huh? Oh, okay. And okay, that's the first time we proved the concept that, okay, how important is the effective exchange coupling between the two phases? How homogeneous you have to mix them? Okay, even in this small scale, the homogeneity will effective exchange coupling. I told you the story where I started the business. The grain size 30 micron, 30,000 nanometers. Now we go down to the several nanometers. Okay. That's the progress. Okay. If you reach the effective exchange coupling, you get 50% of energy density enhancement. Okay. That is another issue, another difficulty. Okay. That's life, always difficulties. Because the chemical methods we used for iron platinum does not work for rare earth material at all. We tried many times, more than 5 years. It's not working. Then I came a simple idea. I asked one of the students to try. He said, okay, if you just do a ball milling, that can be at room temperature. That's basically a room temperature process. Or if you want, you can do it at a low temperature. Use cryogenic. You can use liquid nitrogen, which is cheap. Like you guys are very rich, you can use liquid helium. Huh? Okay. Liquid helium. You can cool down the vial to permitting. However, if you just crash them, you will reach a minimum size. I don't know if you are experiencing this. No matter how long you mill your material, the average size will reach the minimum, then never go down. The minimum is a micron or submicron. Okay, never go down further. Why? Because the small particles will come together again during the movement. Okay? However, if you add surfactants, which I learned from the chemists, okay, then you will get a solution like this. If you don't add surfactants, you will have your solution is just solvent after a few minutes of settling down. Okay, so after we add the surfactants, we obtain in the tube, okay, the solution. The upper part is the small nanoparticles. The lower part is the submicron chips. Okay. Don't overlook this experiment, which has been really important to us. Okay. For nanoparticles, okay, for the first time, okay, we don't have to do the experiment, to do a chemical solution. This is just a mechanical method, mechanical process, right? Use a local solvent. Okay. For the nanoparticles, still for a long time we do not get good coercivity. Why? Because there are so many very small particles got contaminated. Okay. You have to remove all of those things because it's the process of control. One of my postdocs worked really hard for a long time. Then eventually he obtained good coercivity, decent coercivity. Later on, many groups followed this method and reached. We now can make coercivity 2 Tesla. It's nanoparticles. Okay, of the rarest container. That solved a number of problems. We also solved the problem of the alignment. And when talking about the good story of iron platinum nanoparticles of the salt and meaning, I did not tell you the dark side. The dark side is when you have those small nanoparticles with high coercivity, each of them is already ferromagnets. They will stick together. Then you have no chance to separate them. Okay. Even with 20 Tesla static magnetic field, we could not align them. But with these chips, we can easily align them, as you can see from the XRD and the magnetic measurement to highly anisotropic. Highly anisotropic. These are the nanochips we produced with these methods. So we call this as 2D soft magnetic chips, which we can also use to produce nanocomposites. Okay. Then we play with shape. As I mentioned, that shape makes difference in nanoscale. We could produce this iron platinum nanorods, nanowires, okay. This iron cobalt. Well, the early stage experiment has been really challenging because in most cases we cannot obtain 100% on the rocks. Always come with a mixture. Okay? In order to make high quality homogeneous nanorods, you have a lot of trial area. But for the first time with cobalt carbide, okay, the morphology is not that good, however, we get good coercivity. That is encouraging. That means the shape anisotropy will be pretty low. Right? Now let's come to the key parts of this talk. I'll try to finish it in the time. Okay, coercivity puzzles and solutions. As I already mentioned to you at the beginning, I just want to show this slide again. The development of ferromagnets is really the history of enhancement of coercivity. Coercivity we call extrinsic property. You cannot find any lateral materials ferromagnet materials with already coercivity. Okay, you have to bring them to your lab or to the factory to do a lot of artificial work to make it magnetic hardware. Okay, that's the history. Okay, that's the reality. And how the coercivity came from? Okay, first it comes from called the magnetocrystalline anisotropy, which is based on the crystal structure symmetry. Okay, if you have this crystal structure with low symmetry, you have good chance to develop a coercivity because there is crystalline anisotropy. Or you make your sample with shape anisotropy. Okay, a good example is called anicle. Anicle materials is based on the shape anisotropy. However, coercivity is quite modest. Okay, smaller than 2 kilodistance. Okay. And for coercivity, it has been possible for so long. Why? One of the famous paradox in our area, in our community, which has been outstanding for 70 years. It started by Dr. Brown. Okay, he derived this model, this theorem called Brown's theorem, in 1945. It's quite some years ago. Even I did not exist at that time. Say coercivity should be large, or at least equal to this term minus this term. This term is nothing, if you are familiar with micromagnetism, this term is called anisotropy field. This is a field. Okay, you can calculate. This is an anisotropy constant. This is magnetization. Minus Dn is demagnetizing factor. Okay, and this is magnetization. Okay, so that if this is HA is 1 here, then what he predicted is your coercivity should be above this red line. However, practically what we can make this ratio, this coercivity over HA, is far below half, 0.5. Even we tried very hard, but this is some progress. However, there's still much lower than what the lower limit he predicted. So we call this a paradox. Of the community, people in the community thought that this theory is wrong, include myself. Okay, because theoreticians made a mistake too, right? Just like experiments. Okay, and we try to disprove this theory. However, almost all of those people failed because this is a simple theorem. It did not. It's not complicated. We could not find any problem with the derivation. Okay. Then what Professor Kormuller did is, okay, let's put alpha. Okay. Alpha smaller than 1. Then coercivity should equal to alpha of this. However, alpha is purely based on empirical. No one knows how to determine alpha. Okay. Then when I started my postdoc research, my supervisor, Professor Sherman, mentioned this, not just as a joke. He said, okay, your task is simple. If you can make coercivity in a pure iron, so then you have energy product 100 megawatts oscillators, which is tougher than neodymium. Okay, then you can get Nobel Prize. Which was a joke, but if you can do, then it's not a joke, right? Unfortunately, he passed away. He did not see the Nobel Prize last year. Then we tried, as I mentioned, try nanowire approach again. we could control the aspect ratio, morphology, size. Finally, we were able to produce homogeneous copper-based nanowires. Okay, you see the single crystal, single domain, two singles. Okay, that's important. Okay, why? Because the Brown's theorem, the assumption is very clear. Your magnets must be absolutely homogeneous. For 70 years, in my opinion, people never be able to obtain the samples which is absolutely homogeneous. There are always defects because the size, the smallest size, as I told you, is microns or even millimeters. You could not go even smaller. If you could not go even smaller, then you're not homogeneous. So the conditions by Brown is never met. Okay, now we think we meet the conditions. Okay, you see, you measure coercivity. See, immediately when we went down to 8 nanometers, which is the smallest diameter we could, we tried further, but we could not reach further smaller. Okay, then we get the highest coercivity, 12 kilopascals. That's 1.2 Tesla for a cobalt. Could you imagine that? First, I thought this is maybe experiment area. Then we have several students work together to reproduce the results, and the reproducibility is very good now. Okay, now look at the time dependent coercivity. Okay, the thinner, the higher the coercivity. When it's thinner than about 25 nanometers, it crosses the anisotropy field, the red line. It crosses the red line for the first time. Okay, what does that mean? That means the experiment, we experimentally prove the theorem, Brown's theorem. Okay. Before I published these results, I met a theoretical simulation group in a TMS meeting. They already did this simulation. Later on, a Chinese group also did this simulation, which has good consistency. Okay, so basically, if we count the experiment error bar, this belt shows the coercivity ceiling. Okay, this is silly. What that means, I hope I can explain it clearly. What that means is, any sample has geometric conditions, right? Any sample has a shape, right? If you have a shape, your shape already given the coercivity ceiling of your sample, of your magnetic hardening. Okay. We collect many of the data. We think this result shows how you get the highest coercivity of the nanowires or ferromagnet nanowires. Actually, the theory has been understood, accepted for a while. If you make the diameter smaller, then the magnetization rehearsal mechanism will be totally different from the larger samples. The highest possible coercivity is based on the complete coherent switch or rehearsal. Okay. You can think, okay, without the domain was motion, how you make all these spins flip homogeneous simultaneously, which needs huge energy. So that can reach the highest coercivity, which Brown predicted. I hope that's clear. If not, we can discuss more. We controlled the length of the aspect ratio. We found aspect ratio pretty low. As you see, here is the aspect ratio dependence, both simulation and experiments, which is good consistency. Okay. Now, the good news is we crossed the red line. We proved the theory by Dr. Brown. Brown was a very smart guy. He could play piano back sense. He realized before he passed away, what you did is just a paradox. You start paradox. He used this word in one of his papers. With this, I will summarize what we talked today. I hope so we can finish before the midnight, and then you can go to your dinner. We did synthesis characterization of different ferromagnetic materials, mostly focused on those hard magnetic materials, to see what happens at the bottom. Okay, and we observed this strongly size and shape-dependent ferromagnetic properties of those materials, and we experimentally proved this Brown's theorem, which opened the window for the future permanent magnet materials, because the coercivity has been part of the community for so long, for many decades. So with this outset, in the future, we could do materials design permanent magnets for more advanced applications. With this, I acknowledge my colleagues and collaborators and funding. For more details, we have the books. Okay, this is for nanoscale magnetic materials, forwarded by Professor Peter Grumman. He's a Nobel Prize winner. Scamium, this is a new type of magnetic domains. I don't know if you're interested in this. This is probably the earliest book of this talk, forwarded by Albert Fert, is also a Nobel Prize winner. And this is probably the newest book on the permanent magnets, history and future. With this, thank you for your time, and thank you for inviting me.
Any question?
Everything is clear. So,
Any question? So I have two questions. So what do you think about the future to looking for hard magnetic materials with property good enough for application without the errors? Is this still?
oh yeah, this has been a big issue people are discussing, because most high performance permanent magnets are all based on errors. There's some issues with supply, but for Brazil, I don't think this is an issue. If you open the mines,
The problem is to separate.
yeah, separating
That's the problem.
So, in view of economy, we need permanent magnets not based on errors. Okay, because now there is a gap in the permanent magnets market. You can either choose ferrite, which is very cheap, but the energy density very low. Energy product is about 5, or 6 or 7. Very cheap, very stable, however, performance is very low. Or rares, demand board, that's expensive, high performance. There's not much in between. So, in view of the economy, we need materials in between. Then, in view of scientific research, we also need something in between because we want to see without rares, can we create high anisotropy and high coercivity? My answer is yes. That's my feeling. Yeah. So we need more research, especially for these young people. You have time.
And another question is, I didn't know this expression from Brown, but looking at it, maybe it is based on uniaxial anisotropy. That is the reason why in the nanowire you can get this coherently rotation of magnetization. It can obey this expression, and in the book material it's a kind of a mess. Maybe that's why.
Yeah, very good point. So you know all the issues. You know, for shape anisotropy, the long axis of the wires, okay, has to be parallel to the C axis of the crystal structure. That's the easy magnetization direction. These two directions may not be necessarily parallel. Okay, so you have to make them the parallel by control the growth. That's a very good issue. A very good point. Then all those high coercivities measured from the samples of the aligned wires. If they are not aligned, if they are wrong, then the coercivity is only half. This can be explained by Stowe-Wolf model.
Smart idea. Yes.
Yeah.
Okay.
Yeah, good point.
Any more questions?
So what do you think about the van der Waals to the ferromagnets? Do you think it is a reasonable path to look for the van der Waals ferromagnets, like the one with the halogens, like bromide, this kind of, you have a 3D or a 5D ion with magnesium, like a chromium, but they are very 2D with weak van der Waals forces between them. You can defoliate. I think that the classic is chromium, boron.
I heard some of this. I knew some of this, but I'm not very familiar with the theory yet. You know, I think for the kappa magnets, that's possible choice, an approach to explore. I think the weakness of those materials, I think the magnetization may not as high as we hoped. The anisotropy is not as strong as we hoped. But for the kappa magnets, I think it is fertilized. I think it's worthwhile.
Thank you.
Any more questions? Okay, thank you again.
Thank you. Obrigado.